So you see in the opener I made, Jessie wants to cook a very pure product. And as we all know that he doesn't have a PhD, and he even didn't finish his college, I think. But he was able to achieve 96.2 accuracy or purity on the first time travel to Mexico in front of all the PhDs and the engineers. Um, you may ask how he could be able to achieve this. The thing is, first of all, he has a very good teacher, Mr. White, aka the Heisenberg, uh, which who taught him a lot. The second thing I would say is he has the most advanced protocol of the cooking industry. Um, so this is why I want to make the analogy here, although it may not sound appropriate. Uh, Still the same thing for the speech recognition industry. Because the invention of the Wav2vec 2.0, which is the pre-training model, back in 2020, during the past year of 2021, researchers, including speech engineers or software engineers, non-speech people, have been playing around with the pre-trained model released by the Meta or Facebook, and people have achieved a very good result um, because they leverage the best technology developed by these Meta scientists and engineers. Okay, now today, let's take a look at it, the Wav2vec 2.0 and see why it works and how it works. First of all, before I start with the paper, I want to give you a very quick interview on how the deep learning or supervised training works. Okay, first of all, supervised training. So imagine I have a picture of a cat. And I would, for instance, pass that through a deep neural networks. Okay, and then I will get a recognition output or classification output. It's a cat. Okay. So this procedure in training is called a supervisor training. So I can have many different types of uh, black cat, white cat, fat cat, old cat into this trainer, and they all have the label cat, right? Um, or the cat is a label. But my question comes, what if the label stuff is gone? Or say no label? So here, this is called what? This is called unsupervised training. Unsupervised. So the input is still here, but the output is gone. And now this is what the Wav2vec people are doing. It's a branch or of the unsupervised training. what they were doing is instead of having no labels which couldn't start training, they managed to develop certain types of um, they call that, I think the word is called let me quickly look at the exact word they were saying. Okay, they are calling this thing called discretized output of the feature encoder. Well, this may not be very straightforward for you, but I have a simplified word for it. Code book. You may ask me, wait, what is code book? What they are trying to talk about? Let's first start with um, language in the South India, or it's called Tamil language. Or Tamil speech recognition. Okay. Unlike English, which you could be able to get um, hundreds of hours or even tens of thousands of hours of speech recordings with human transcriptions. For Tamil language, it's very hard, first of all, to collect such amount of speech recordings. And also, it's hard to find qualified people to transcribe those recordings. So, what people were doing in the past, they were developing some type of things called acoustic unit. So, what is this concept? So for English, acoustic unit can be attached to the concept of defined by the linguisticians. Okay, so you all know this, right? So in English, um, acoustic unit is phones. So according to the linguisticians, English can have this is the most common thing. Okay, they agree that there are 39 phones. For instance, it's B, P, T, or I, A, O, etc. Right? But some people are saying there are 61 or even are different numbers, or there's something called 48. But it's a trivial. It doesn't matter. It's sometimes some variations of some phones, given some context. But the thing is that linguisticians has defined all of this. But let's look back at the language, Tamil language. Okay, it does not have any linguisticians who has defined these phones for Tamil before, probably. Um, this is why I think back in about 10 years ago, people were using some type of thing called clustering. And also, it's called automatic clustering, right? So what they were doing is that, um, first of all, they get uh, features of Tamil language. So, for instance, for each frame or each segment of a recording, they would use either PCA or whatever type of feature dimension reduction method, so that they can project the features distribution. For instance, MFCC, right? MFCC is a common feature extracted from the raw waveform, which can represent the vocal tract movement. They would be able to find, okay, for instance, they projected to use to the PDA to project it to 2D space, okay, 2D. And they found that, okay, on those spaces, it's very obvious or somewhat obvious that these projected features can be seen as clusters. Okay, then they run this type of automatic clustering algorithm, and they generate clusters of features, and then they attach this to the original concept of phone. Okay, they say, although we're not linguisticians, but we can say, okay, this is what probably what the Tamil people are speaking in, especially the same thing as the concept that we have as phone. Let's call them phones, okay? So probably in this way, they can automatically find phones or acoustic units. So they would be able to extend it from here. You all know that in English, the word is, each word is a composition of phones. So in Tamil language, they can also do this. They can define words is composed of acoustic unit. And the words, it got sentence got paragraph. In this way, they build this bottom up hierarchical Tamil language station information, whatever. They were able to build these type of linguistic structures, so they can use the model that is being used to train the English speech recognizer, apply this to Tamil language, do everything like people did in English. Okay, but now it's 2020. You may say, are people still doing the acoustic unit? For me, I see people were still doing the same thing, still. But this time, it's being done in a more sophisticated way. So remember in the past, when people were trying to find this acoustic unit, they were basically doing automatic clustering without any feedback loop. So it's straightforward. And what is the criteria for, people may ask, okay, what's your criteria for stopping your clustering? How do you define your distance? So it's very ad hoc or rough. But nowadays, in Wav2vec, they are capable of doing two things. First, they were able to develop a very good representation of distance. Distance between the AUs. Well, the second thing is that they apply this type of acoustic unit learning thing or clustering thing in a deep learning framework. So what's the benefit of doing this? The first thing, as we all know, you're capable of leveraging a great amount of data. Big data. Okay. Or the second thing is that you're gonna be able to use the backpropagation algorithm. So the beauty of the backpropagation algorithm is that you're gonna be capable of have a feedback loop based on how well your clustering is. You can adjust the acoustic units you learned and then make this clustering procedure to be better or learning procedure to be better. Okay, please keep in mind the acoustic unit is my understanding. Wav2vec paper never talked about anything about this acoustic unit, but the term is only created for you to understand or to better understand the Wav2vec paper. Okay, let's take a quick look at the paper. Any questions so far?
Yeah, so one quick question. So the backpropagation algorithm, you're able to do it because of one, right? Because you have a distance metric, you're able to define a loss, and therefore you can apply backprop. Is that right? Or
Exactly, yes. Or loss, same thing. Backpropagation always comes with loss.
yep.
When
Yep.
there's a loss, there's a backprop.
Right. And
Okay.
and you're able to define the loss because you have a distance metric.
Because I have. Yes, you're right. Because I have the distance.
Yeah.
You're exactly
Because
right. Thank you.
without one, you cannot do two.
Yes. Loss goes backprop. Backprop, helps it improve the AUs. You see, you have a circle loop. So this is how you're gonna improve your learned acoustic unit iteration by iteration. Okay,
Yep.
great. Okay, um, I would say Wav2vec 2.0 is developed on the basis of a Wav2vec 1.0 or Wav2vec. So this is why this paper, the author didn't go much into the details. And I didn't, I was also not trying to go into the details of the paper. The only thing, first of all, I would want to give you a very quick or rough description of the model in this Wav2vec model. Here I showed another paper called the Big SSL. You can search the Big SSL in the OLED Wave YouTube channel. I have a very long tutorial on this. Hopefully you won't get asleep while watching that one. And this paper has a very good diagram of the network structure or network flow or tensor flow of the Wav2vec 2.0 model. Let's start from the left one first, or the standard training. This is a typical feed-forward neural network. I would say the details are trivial. All you have to say, okay, I have a feature, input feature, okay, and this, the black, yellow, white, green stuff, I call this DNN model. deep neural networks model, okay? So I got a context vector. Okay, I can use this context vector for my you can say can be an encoder, right? The encoder's output can be used for decoder or other downstreaming tasks. Okay, this is called a feed-forward network. And now let's see the diagram on the right. Again, you don't have to know the details right over here. Okay, now you look confusing to you. All you have to do is okay. This is still same as the right. It's still the context vector. And this is the DN, right? And this is the input feature. So you say, wait, what's the difference right here? So what's this really different is the stuff on the right part. On the right part, you can see I will still forget about the encoded convolutional sampling. I just draw something from here, okay? It's not right, but I just help you to understand everything. So I simplify the stuff. So you pass through this through into something called a quantization module. So the input feature after quantization, you got what? You got a target vector. Remember the target vector or target context vector. So you can imagine, like I mentioned before, the quantization or the clustering process is always a process of generating a code book. So what does a code book look like? Suppose you have a two-dimensional feature space. Suppose the feature only has 2 dimensions. Okay, the code book would be looking like this. For those of you who have taken the information theory or ML class, you know what I'm talking about. So you see, the black dot in each region is the centroid of each code, and each region is a code. Okay, this is a two-dimensional feature space. I have a one code book. And you say, wait, how does this code book work? So suppose I throw a feature sample into this feature space. This is my throw into the feature, the plus sign. It falls into this region, and this feature, let's call that X, would be converted into a code, which is exactly the quantized code of this one, QI. Okay, so you can ask, wait, if I suppose throw it here, still QI, right? Any feature falls into this region would be quantized or have the same output value QI. And this in the Wav2vec paper, it's called context target vector. And here, and you may see that it solved the definition. You may ask, how do I solve the problem of defining the loss? Here, they leverage the contrastive loss. So in the contrastive loss, you may say, definitely it takes the context vector as input and also the target context vector as an input. So definitely, so because we have defined the distance, what? We have this code book, right? So keep in mind, whenever you have a code book, you have defined your distance. Otherwise, you won't be able to run your clustering, right? You have the code book. And then you have your distance defined. So all you have here is, let's call this Z, and I call this Q, okay? The contrast loss is simply can be regarded as a distance between the context vector Z and the target vector Q, okay? So you may ask, Wei, so definitely you want to minimize this loss, right? Everybody knows that you want to minimize the loss. So what's the purpose of defining this contrastive loss? So my understanding is that it's smart because whenever you want to minimize this loss, you can see the back propagation would go this way all the way into the neural network that generates the Z and update or upgrade the parameters in this DNN model unless it reached to the input feature. And it also, because on the right side, there's also a path from the input feature to the contrastive loss. There's another backpropagation procedure. Go back to the input feature. So in this backpropagation loop or path, it would update the model for doing the quantization. So you can see by minimizing the contrastive loss, it not only make the model DN right here better, but also make the quantization better. So it tries to improve both things, right? And definitely it solved the target issue. This is the biggest contribution of, I think, in this proposed Wav2vec model, because for pre-training, you don't have labels or you don't have human transcriptions. And remember, in pre-training, people don't run recognition to get pseudo labels. So no pseudo labels. So this is how you should generate some label, but you can't use a seed model to run it because that way it won't be a pre-training. Okay, so this is why they use this type of a clustering, you call that, or quantization thing you called, to generate some target for the contrastive loss. And this is very smart. And the difference of the Wav2vec model compared to the traditional automatic clustering method or codebook generation method is that this one is just a feed forward, no backprop or no feedback loop. You run one iteration or two iteration, you maximize some likelihood. That's it, right? But this one, you have this backprop. You can upgrade your quantization model's parameter to make it better and better based on the loss. Okay. I think now let's go into further details to see what is going on in this model. Yeah.
Wait, can I ask a question?
Yes.
What about the masking that they have in that other figure that you just showed?
Okay, that's a detailed question. Let's see the mask here. So I think you were talking about the masking over here. It's hard to see my mouse,
Yeah.
but it's here.
And also they talk about like context vector from masked features.
Right. So all it does is remember in a BERT model, you have this type of a mask language model technique. So this is the author that are trying to do similar things here. But I don't think the traditional or the original Wav2vec has this mask. But this one is maybe the Google author add this thing to it. But it's easy to understand. All it does is that suppose I have a waveform, and this, and suppose I extract a feature like this. Okay, this is my feature. I can train my model or minimize the contrastive loss without doing the masking, and that, but I can also mask a certain segment in my original feature and see whether I can still minimize my contrastive loss. So my understanding of doing the masking during training, especially for speech, is trying to prevent the model, or this time the pre-trained model, to go into the status of overfitting. But today I don't really have a lot of time to go into the details why it can be good for preventing the model from being overfitting. I think let's look at the quantization module, because if you look at the DAM part, I think if you just spend some time, you can understand it. You don't have any issue. Let's see the quantization. They invent, or they buy something called a product quantization. I think you have to read the Wav2vec paper, and I'm not gonna go into the details, but product quantization is, I think, very straightforward. You would be able to understand it. The only thing is that the new thing is that, look at here. Here, I just have one code book, right? The meaning of the product quantization, I think, is that you can have multiple code books. So basically, by doing different, I think it's better to take a look at the Wav2vec paper. I have it. I do. I think they're too much mess. I don't think I have time to go into the details. Um, but I think all you have to remember is that um, the concept of product quantization is that simple. It has multiple code books. So these type of multiple code books can contribute to the final coded features. I would name that as or comprehend it as a soft code book. And I personally wonder whether just the one code book work. Because if you look at the paper, Hubert paper, Hubert developed after the Wav2vec 2.0. I think the Hubert only has one code book other than multiple code books. And after this type of multiple code books over there, the author was very smart to design or introduce a softmax called a Gumball softmax. I also won't go into the details. But the good thing of the Gumball softmax is that it's differentiable, because I think this is the first time the author made the codebook model or generation module to be differentiable. And let's take a look at the loss. So remember the loss has two parts, right? The left part context vector, the context target context vector from the quantization. And same thing here. If you look at equation number 3, so you want to minimize the loss, right? And this is a minus sign. You want to maximize this. Maximize this. So the sim means cosine distance. So you want to maximize the cosine distance, which means you want the CT and the QT to be as close as possible, right? So the CT is your context vector, and the QT is your target context vector. In this way, you can see after training, the CT and the QT would be more close together. And you may ask, wait, what is on the denominator? You want to minimize them. So given the context vector and another or other context target vectors in this batch, you want this context vector to be away from other context vector, which makes sense to me. And remember, the final loss is in equation 2, has two parts. The second part is the regularization term. Regularization term, how it was defined. It's called diversity loss. So for those of you who know a little bit about codebook, it's very easy to be understandable to you, because all they was doing here is they're trying to maximize the entropy, or say they wanted the codebook to be distributed, how to say that word, more evenly. The more evenly you distribute it, not concentrated on one certain location, the bigger the entropy you will get. Okay. That's what it did. It's a regularization term. I think it's okay for you to train without the regularization, but the author said you should train with regularization. But in my personal opinion, suppose you have a lot of data, maybe you don't need this regularization term. Okay. Fine-tuning data set, I would just skip all of this. I think it's very straightforward. They played on 60K hours of data set. So you may ask, wait, what's the concept of 60K hours of data? Let's do some math here, right? Suppose I speak non-stop for 24 hours per day. So the common data set which is being used in speech recognition community is called the LibriSpeech. How many hours does it have? It has 1,000 hours, or see, or indeed the training set is 960 hours. So I suppose every day I speak 24 hours without stopping, no sleeping. I have to speak 40 days, 1.5 months. Okay. Suppose I only talk 8 hours every day, or say I study English by listening to other people talking. Okay, so say every day I spend, say, let's see, I spend 4 hours on 4 hours on listening. Okay, so how many days is this? I think it's 240 days. So which means I listen to other people talking for almost 10 months. Okay, but this LibriVox dataset, I think it's not LibriLite or LibriVox. It has 60K hours of data. So I listen 4 hours every day. Then I have to listen 150K days. That's suppose I divided that by 30 days. So that's 500 months, right? And then if I divide it by 12, that's how many years? I think that's about 40 years. Wow. So suppose I listen every 4 hours audiobooks of the LibriVox dataset every day. I have to listen 40 years. It's very long. That's a very large dataset, I have to say. So how many days they end up training the model? I think they have something. Okay, look at here. They train on 128 V100 GPUs over this is 108 V100 GPU. So let's talk about the price you have to pay to make this training cluster or training happen. So NVIDIA sells DGX machines. So each DGX machine, DGX1, I think, has 4 GPU, 4 V100, and each machine will cost you about $50K. So 128, this equals to 32 DGX machines. When you multiply this, I think this is The total price is let's do this. Move this. $1.6 million. Okay, their configuration, only the GPU machines, it will cost them $1.6 million. When they trained on the 40 days of speech, not 40 days, on the Libre speech data set, 1,000 hours. It takes them two days. That's fast. But when they train on the LibreVox dataset, which is 60K hours, I think they use some acceleration or something, so it's not linear. It costs them about 1 week. So you get a general concept how they are doing. About the result, I have to say the result is very good. You can see on the test set, they're able to achieve 2.0 by using fairly fundamental model. I don't think you use any very sophisticated decoder hook up to the encoder. Oh, okay. Let's talk about how they use the pre-trained model. Okay. Okay. So once you trained your context vector, see here. So what they would do is they would discard the contrastive loss module and the quantization module, and only use this context vector from this DNN as the subsequent model's input. So let's see this. What they would do is this: after they throw away the right part, they have this input feature. They have this optimized DNN, and now let's call this encoder. Encoder can be very large, I would say. It can be, for speech, it usually can be about 20 layers, 24 layers, large one. And then they got this type of context vector, okay? And so now they can do the transformer, right? They can add another encoder on top of this, and have this connected to the decoder, right? This is a standard transformer. And this time, it's supervised training. So after you finish the pre-training, you hook up this to the input of the transformer's input, encoder's input. So then you train that using a supervised style. Have the output Y. So the back propagation would go all the way from here to here and here to here. Of course, this is, you have this type of cube. I think they have some cube over here. So you may ask, wait, so you in the supervisor training, you update this decoder? Yes. You updated the transformers encoder? Yes. And how about the pre-trained encoder? The answer is you could either update it, the encoder's parameter, or keep it fixed, not change. So you may ask, when should I change? When shouldn't change? Well, in this paper, I think they changed the encoder's parameter. So, and this whole procedure is a supervised training, but it is also called a fine tuning. On a specific task. Why? Why they call it fine tuning? Because this encoder or the pre-trained model is trained on the 60K hours of unlabeled speech data, right? But the supervised training or fine tuning is only leveraging 1K hours of labeled data. This is Libre speech, right? This is Libre Lite. You can see these two datasets are two different datasets, and the Libre speech is your task. Okay. And then what is also very interesting to me or to most of the researcher is that although for using the full-size Libre speech training set, you can get a very good result. But suppose you only have 10 minutes of labeled speech. Let's see, so right now I don't have 1,000 hours. I only listen to some transcribed speech for 10 minutes. They can get a word error rate of 4.8%, which I would say if you convert this 4.8 to accuracy, this is 95.2%. And the best thing you can get is using the pre-training is 2.0. This is 98%, right? You know, for speech recognition, in my personal opinion or my personal experience, 95% and 98%, suppose there are two recognizers. For me, I won't notice a difference. So this is really, you know, surprise lots of people. So what does this mean? This means that, so when you met a new language, okay, let's say Tamil language, yeah, Tamil language. What you can do is that you can go to the Tamil plaza or community. You can record tons of data. Say you record 60K hours of Tamil language or speech, and then because you cannot find expert to label all of them, and then you find some expert from Harvard University, and he only labeled 10 minutes for you. I think it's very likely for you to use this Wav2vec pre-training plus fine-tuning procedure to get a recognizer which has accuracy above 90%. Mark my words, I think it's gonna happen. So this is a very good thing, because in the past, before the pre-training model was introduced, to achieve a accuracy which is higher than 90%, you at least have to collect at least 1,000 hours of labeled or transcribed speech, which takes a lot of effort. For Tamil language or some rare language in the world, it's impossible. I think they further try the conformal model. No, sorry. I think the homework was done by somebody else. This is fully supervised training. The best result we can get back in 2020, which is 1.9. So the model is way sophisticated or bigger than the model used in this unsupervised learning. What I meant is the conformer. I mean, this part, conformer's parameter is way bigger than the model used here. I think they just use some their encoder in this Wav2vec paper. Their encoder is smaller than the conformer model. The conformer model, the encoder is very large. But the unsupervised learning part, this encoder part, the conformer doesn't have. So I think eventually the model in this work, Wav2vec, the model is still bigger than the conformer model. Okay, they did some subtasks. I will skip this. And the conclusion, I think, like they mentioned that, first of all, you can do a supervised training, and then you can achieve a WER, very good WER, by using not many amounts of labeled speech. And then they are talking about impact. Think about there are about 7,000 of spoken language in the world. Suppose you want to build a AI or speech recognition application for each language. So think about this beautiful way of making